Hi there, this is just a mini tutorial about combinatorics, mostly with the intention of refreshing on the notation of combinatorics, which is just the part of math that deals with counting the number of ways you can arrange variables in a set, which doesn't sound very informative, but most of what we need to get through is to remind ourselves a bit about factorial notation, and then I'm going to talk a bit about permutations and combinations and the ways that we have to count them. Permutations and combinations both deal with counting up how many ways there are to arrange numbers in a subset. The major difference is that in a permutation, order matters. Combinations, order does not matter. The best way of thinking of this for me is if you're playing poker and you've got 5 cards in your hand, it doesn't matter how many permutations, how many arrangements of those 5 cards you have. You could shuffle them around in your hand no matter how much you want. That's the same poker hand. All 5, those same 5 cards, the same set of 5 cards is one combination, one poker hand. So the order does not matter. Whereas if I have 7 numbers and I'm trying to call my mom, the order of those numbers does matter. There's only one permutation of the 7 digits in my mother's phone number that actually allows me to call her in particular. So a phone number is a permutation, a unique permutation of the one combination of 7 numbers that is my mother's phone number. So starting with factorial notation. Factorial notation is the exclamation point, which is part of why combinatorics was combinatorics. When I was in high school, I missed class one day and I went back the next day, and in my math class, the blackboard was covered in exclamation points and I was so confused. So factorials have always stuck with me as a kind of a confusing surprise. And they still look to me like they're just really excited. Anyway, n factorial is defined to be n times n minus 1 times n minus 2 times n minus 3 times, times all the way down n minus times 1. So for example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. Any number is itself times all of the whole integers lesser than it, up to and including 1. Now that that's out of the way, I can talk about permutations. So a permutation is just an arrangement, and so when we're calculating the number of permutations you can make of a set, we just want to know how many different ways you can arrange the things in the set in order. We're going to start with letters, and we're going to say, for some reason I have the letters A, B, C, D, and E, and I want to know how many different ways I can make permutations of those 5 numbers. So this is one permutation, A, B, C, D, E, and I could have A, C, D, E, B. That's another permutation, a rearrangement of the letters. And there's, I could just write them out and count, but for larger sets, that's impractical. So the way I admit I do all combinatorics problems this way is I say, okay, so if I'm making permutations of 5 letters out of my possible set of 5 letters over here, that means I've got 5 slots that I can put my letters into. And I'm choosing letters from my set over here to put into my subset over here. You hear the word choose a lot in combinatorics. You're choosing permutations from your set of variables. So when I'm choosing the first one, I've got 5 possible options. Then when I'm choosing the next slot, well, I've only got 4 left. And then for the third slot, I've already used 2 of these, so I've left 3 left, and then I'll have 2 left, and then I'll have 1 left. So that looks an awful lot like 5 factorial. And just to prove to ourselves that it's true, what if I've only got 3 spots and let's say I'm only using A, B, and C. Then when I'm filling the first slot, I could use A or B or C, so that's 3 options. No matter which one I've picked, there's still only 2 left for the second spot, and then only 1 left for that spot, so 3 factorial again. So if you're making permutations of size n, the number of permutations is n factorial. Well, what if I'm making permutations of size 3, and I've got 5 letters to choose from? Well, in the first slot, I could pick any one of those 5. In the second slot, I could pick any one of the 4 that's left. And in the third slot, I could pick any one of the 3 that are left. So that's 5 times 4 times 3 permutations. If I want to get a general expression for that, this is the same as 5 times 4 times 3 times 2 times 1, divided by 2 times 1, right? Those cancel. But I'm putting this 2 times 1 on the bottom so that I can get a nice expression for 5 factorial on top divided by 2 factorial on the bottom. Which, if we're thinking of, in general, the number of variables I'm choosing from is n, and the number of slots I'm choosing them into is k. You get the general formula for permutations, which is, where can I put it? And there's a bunch of different ways of writing this down. So this is one way, NPK notation. So the number of permutations of size k taken from n variables is n factorial divided by n minus k factorial. Right, because if you remember down here, that 2 is 5 minus 3. The number of variables we started with minus the number of slots we had. And another way you might see this written down is PNK. Now that we've talked about permutations, we can talk a little bit about combinations. The difference between permutations and combinations can seem a little bit subtle, and I know I mix it up all the time, partly because we use the word combination in English to mean something a little bit different than what it means in combinatorics. Actually, we usually use, I think of the word combination in English to mean kind of what permutation does in the maths. Anyway, the difference between permutations and combinations is whether or not the order matters. So, going back to my sticking letters into slots example. In permutations, order matters. So if I'm making permutations, right, A, C, B, E, D, those are 2 different permutations. In combinations, order does not matter. So if I'm trying to count the number of combinations I can make of these 5 letters in 5 slots, it's actually a really boring thing to ask because there is only one. Because A, B, C, D, E is because order doesn't matter. No matter how many permutations I make, it's one combination of 5. So combinations are only interesting if I have if n is different from k, right? N, the number of variables I have to choose from, and k, the number of slots I have to put them in, they have to be different for combinations to be a meaningful question. Let's say I've only actually got 3 slots. So I want to know how many combinations of 3 letters I can make from a set of 5 letters. Well, we can start the way we do with permutations by going, okay, well, if I'm filling in this first slot, I can choose any one of the 5. And in the second slot, I can choose any one of the remaining 4. And this one, I can choose any one of the remaining 3. That's great, but that looks a lot like the number of permutations we can have. So we're missing, we've double counted all of the ones that have actually the same set of letters. So, for example, I need to make sure that ABC and ACB, those only count as one combination, but in this 5 times 4 times 3, they'll get counted multiple times. What I need to do is take the number of permutations I can make with my set of n, and I need to subtract the ones that are repeats, that are the same combination. So a way to get at that is to ask, for each unique combination, how many ways can it be reordered? How many different times will it appear in the set of all possible permutations? Right, so A, B, C, A, C, B, B, C, A, B, A, C, C, A, B, and C, B, A are all the possible permutations of this one unique combination of 3. An easier way to do that would have been just to say it's 3 factorial, because the number of ways of permuting a set of 3 things is 3 factorial. So the number of combinations here will be 5 times 4 times 3, all divided by 3 factorial. And I'm going to skip straight to the general case, where n choose k is also written most of the time like this. That's how you'll see n choose k written. And it's the familiar formula for permutations with an additional division by k factorial. Right, because in this example, n was 5 and k was 3. And I want to mention quickly an assumption I was making when I derived those expressions for the number of permutations and the number of combinations you can make from n variables into a set of k. And I'm assuming that after you do your choosing, right, I've got my slots and I'm choosing things to go in them, I was assuming that once I put something here, that whatever I put there has been taken out of the set of options forever. One way to think of this is to imagine you have a bag of ping pong balls with numbers written on them, like they used to make lottery numbers, right? So I've been assuming that every time you take a ball out of the bag with a number on it, it stays out. It's not getting put back in the bag. So there's no replacement into the set of possible numbers you can choose. Most of the time, that's the case we're talking about when we do combinatorics. So that's why those are the 2 formulae I showed you. When you start adding replacement, which would be every time I choose a number out of the bag, I look at it, I write it down, and then I put it back in the bag. So I could choose it again on the next round. And the most obvious thing that I think about with replacement choosing is DNA, right? If you've got a gene that's 200 base pairs long, at each base pair there's going to be 4 nucleotides you could have there. So if you're trying to figure out how many possible variants you could have of a 20-letter long stretch of DNA, you're choosing out of 4 at every step, so you're choosing with replacement. Permutations with replacement are fairly straightforward, because let's say I've got my 5 letters again, and I've got 3 spots, but instead this time I'm choosing with replacement. That means for the first spot, I've got 5 to choose from. For the second spot, I've got 5 to choose from. And from the third spot, I've got 5 to choose from. So if n is equal to 5 and k is equal to 3, so the number of sets, right, with replacement is going to be n raised to the power of k, because it's 5 times 5 times 5. In the gene example I was talking about, right, if you have a gene that's 20 base pairs long, which is nonsensical, it wouldn't be a whole gene. If you have a sequence that's 20 base pairs long, the number of possible variants you could have is 4 to the 20th, because there's 4 base pairs available for each one of those 20 spots. So it's a lot. As for combinations with replacement, that's actually kind of a complicated mess. It's kind of a complicated mess, and a lot of combinatorics is devoted to specific problems of when there's combinations with replacement and different kinds of sets and different kinds of replacement allowed and different kinds of repetition allowed. And So we're just going to kind of leave combinations with replacement out of it for now. So in summary, factorials are really excited numbers that are themselves times all the numbers, all of the whole positive numbers smaller than themselves. Permutations come in two flavors: without replacement npk is equal to n factorial time divided by n minus k factorial. With replacement, npk replacement is just n raised to the power of k. And combinations, where order doesn't matter, n choose k, which is usually represented like this, is the same as permutations with an extra k factorial on the bottom. And the major difference is that with combinations, order doesn't matter. N is the number of things to choose from, and k is the number of slots you're going to put them in. So that was my race through basic combinatorics. If you want some more in-depth explanations of how the equations for permutations and combinations are derived, or want to see some more examples, I'm sure there are some external resources to be found quite close to this video.